Hello, this is Shayan, and I am back with another video about strength of materials and structural engineering problem solving. So, today's topic, we're going to talk about combined loadings, in particular normal stresses, which is going to be a combination of axial stresses and flexural stresses that we're going to discuss. So, let's see how we're going to solve this question. So we have a question that says determine the normal stress distribution on a transverse section at corners A, B, C, D of the rectangular prism subjected to loads as shown. So here you have this 15 kilonewton, 30 kilonewton, 10 kilonewton, 40. Good, some random forces. And then it says additionally draw the corresponding stress distribution diagram and determine the line of zero stress. Okay, so of course initially our objective is to find what the stresses are and then of course draw those stresses correspondingly. So here again, the idea is normal stress distribution. As I mentioned, so we have axial stress. In this case, of course, again, the normal stresses that we are discussing are axial stresses and flexural stresses. And as you can imagine, axial stress, like a column, it can be applied right in the middle like that. And like flexural stress can be about both axes here, right? Again, we don't have like the y axis here, so we're going to discuss all of these axes later, but we don't have twisting, that's like shear, so we're not really concerned about that. The only axis we are concerned with in this case is like this axis maybe, and this axis. So we're going to go through the steps and how we can kind of make the question easy for ourselves. Okay, so let's move on. As per the other questions, other videos that you've seen, I have some steps for you again to follow. So initially, we're going to identify some arbitrary perpendicular axis. So as I mentioned, the x, z, so we're going to do that. Then we're going to separate each load case and determine the resultant moment and axial force on the cross section about both axes. So it's again very similar to a method of superposition for calculating the deflection. So initially we're kind of separating all the load cases and then at the end we're going to combine them together. In step 3, we're going to add all of the loads considering their direction, as I mentioned, along the longitudinal axis and about the bending axis. So we're going to add the axial forces together, and we're going to add the flexural stresses about each axis. In this case, it will be like the xx and zz separately. And then we're going to find the axial and bending stresses based on the formulas we know. For example, the axial stress formula is just, force divided by area. And for stresses, again, my over I, the famous formula that we have for flexural stress. And then we're going to find these stresses, kind of combine them together after finding them, right? So you have the axial, you have the flexural, and so forth. And at the end, we're just going to draw the stress distribution, which is, again, just kind of like a schematic, just presentation of how everything looks like on a cross section. So let's start with our step 1. So these are the loads that we have. Great. So we're just going to follow our steps like a computer. So here, step 1, identify the arbitrary perpendicular axes that we're going to work with. So in this case, what I'm going to do, I'm going to say, okay, you know what? This is xx, this is zz. It's completely up to you. The terminology is up to you, but of course, as you can imagine, when you have these perpendicular axes and they're perpendicular to the section as well, it makes our life a little bit easier. And that's how we are going to calculate the normal stresses. So this is the xx and this is the zz axis. You can call this zz, you can call this xz, you can call it yy, up to you completely. So that's the first step. In the second step, we talked about separating each load case and determining the resultant moment and axial force on the cross section about both axes. So how are we going to separate them? So let's go ahead and do that. So I'm going to say this is force 1, P1, that is P2, that is P3, and that is P4. Okay. So one by one, I'm going to kind of, again, you see, I've separated, I've isolated this load. You don't have to do this like every time, just draw the whole thing. You can just draw the whole, just a rectangle on the top. It's good enough. And you're going to say, okay, this load, what is the, how can I account for its flexural effect and axial effect, right? Because I know that at the end of the day, this is like kind of pushing this like kind of, block down, right? So you have kind of a, compressive force here, but it is applied with some eccentricity with respect to the axis. So like there's an eccentricity here and there is an eccentricity here. So it does also create some moment about both the xx axis and the zz axis in addition to the axial force that it has. So how can I deal with that? I'm going to say, okay, what I can say, okay, the 15 kilonewton is going to be there. So if I want to convert this 15 kilonewton force to an axial force, well, I kind of like account for its axial force. I'm going to say, you know what? I'm going to bring this eccentric axial force to the middle, make it concentric. But what I'm going to do for, just calculating its effect flexurally, I'm going to say I'm going to take into account its moment effect as well. So 15, I brought it to the middle, as you see here, right? But I'm going to also say this creates a moment in this direction about the x-axis axis. Why is it this direction? So you can imagine that this is kind of this 15 kilonewton about the x-axis. It's pushing on this side, right? And it's pulling it from this side. Pushing here, pulling here, right? And that's why the moment looks like this. You see here, I'm pushing here, I'm pulling it from here. Pushing, pulling. And again, push and pull here, it's going to be important when we are going to determine our signs for compression and tension and so forth. So keep that in mind. Again, since this concept is very important, I'm going to just emphasize it one more time. So you have 15 kilonewton here applied, right? You're pushing it here, pushing it down, right? About this axis. Forget about the ZZ. Forget about the, it's like you don't see it now. XX, pushing it on this side, pulling it in this side. That's why you see like the moment looks like this. And then same thing about the ZZ axis. So you see about the ZZ axis, now imagine that the XX does not exist. About the ZZ axis, it's pushing on this side and pulling from this side. Pushing it in, pulling from here, okay? So you see like my arrow is kind of pushing in that direction. One simple thing you can kind of, remember to kind of simplify everything for yourself. In any direction it is pushing, that's the direction. See like the arrow is going in this direction. That means that the arrow is going to go for the ZZ axis in this direction as well. For XX axis, the arrow is going on this side, so the arrow will go in this side as well. So that's one simple thing you can kind of keep in mind to make it easier. So these are the directions. Now, what are the values? In this case, the axial force is pretty obvious, 15 kilonewton. Great, so that's my axial force there. And it is compression. And in this case, if I want to find my moment, I have to know what my lever arm is. Do you remember what moment was? Moment was force multiplied by the perpendicular distance from the axis. So in this case, my force is 15, great, but what is my distance from the x axis? In this case, my distance is 200 millimeters, okay? So remember that in some cases in the exams, maybe you are going to be given, let's say, this 200 millimeters, which is the distance from the edge, or this 150 millimeters, again, the distance from the edge. What we are concerned with when we are calculating our flexural values or like moment values is like the distance from the axis itself, okay? So as a result, I can say that my whole distance here is 800, half of it will be 400, so the whole thing here is 400. As a result, 400 minus 200 is gonna give me my lever arm. So this is what my, how I can calculate my moment. So force multiplied by distance. But remember also that this is like distance is millimeters, so I'm going to put it in meters. So I'm going to say 15 kilonewtons times 0.2 meters. I'm going to get my resultant moment from this force about the x-axis. I'm going to do the same thing about the ZZ axis. So here, what is the lever arm? So this is the ZZ axis. This is the force. The perpendicular distance is this much. Again, not 150, but in this case 50. Why? Because 400 millimeter is your whole distance. Half of it is 200 millimeters. And from this half, the 200, you subtract 150, you're going to get 50 millimeters. So in this case, what happens is 15 multiplied by 50 divided by 1,000. You're going to get the amount of moment from force P1 about the ZZ axis. And after this, we're going to repeat kind of the process that we did for other types of loads. So let's say in this case, you have a load that is kind of pulling on the cross section, right? So at this point, I have a 10 kilonewton load that's kind of pulling. Again, it's the same idea. We're going to, again, make the force initially concentric, but we're going to take into account its moment effect, basically. So how we can do that is, as you can see, okay, I'm going to bring the load in the middle. It's going to be concentric. Simple as that. It's going to be 10 kilonewton. Then I'm going to say, okay, this load creates moment about, again, both axes. It has eccentricity about both axes. So about the XX, it has an eccentricity. And about the ZZ, it has an eccentricity. So as a result, I have to account for the moment about the both axes. So what I will have about the XX, as you can imagine again here, I have pulling here. I'm pulling it. As a result, since I am pulling this, this is, again, the arrow will go here. So like you can imagine like this arrow kind of coming like this, right? So it's pulling from here, pushing here. So that's why, again, I have drawn my moment like this. Pulling from this side, pushing to this side. Simple as that. Same thing is going to happen for ZZ, by the way. So about the ZZ axis, you're going to say, okay, I'm pulling from this side. See, I'm pulling from this side. I'm pushing to this side. So the arrow is going to go to this top part. So you see, the arrow is going to the top part here. Okay. So the visualization of this is very important. Now we can just put the values. So I know that, okay, I have 10 kilonewton force, but in this case, of course, it is tension. I'm pulling this section, right? And then I have my flexural force, so the moment force, and the lever arm. In this case, it is pretty clear. So because in this case, you have 10 kilonewton and you have 400 millimeters of lever arm. Again, the perpendicular distance from the x-axis axis. So 10 kilonewtons multiplied by 0.4 meters or 400 millimeters. So in this case, again, remember that the units we're using is kilonewtons and meter, right? That's like the most common units that you have for moment. And so 4 kilonewton meters here, and same thing for the ZZ axis. So in this case, you're gonna have kind of this 2 kilonewton meter force because you have this 10 kilonewton force and you have the lever arm, again, the perpendicular distance from the ZZ axis, which is 200 millimeters, or in this case, 0.2 meters for us, right? So that's how you get your moment as well. Now, these were kind of the forces that we had applied on the cross section. In other words, these were the forces that were normal to the plane itself, normal to the plane ABCD. However, let's now kind of think about the lateral forces, like this force, P3, 40 kilonewton applied kind of in the ZZ direction. So the first important thing to take away from this is, of course, this does not create any axial force, right? So you see, like axial force, we would just call it if it's like perpendicular to the axis itself. Sorry, perpendicular to the plane itself, right? Or like along the longitudinal axis that we have. That's what we call the axial force. But we don't have anything in that direction. It's going to the left, right, you know, in the direction of ZZ. So that means that this does not really have any axial force for us, right? No axial force. But it does have moment. It's, as you can imagine, it's kind of trying to do this, right? It's kind of trying to kind of pull this one. So if I put this here like this, it's kind of trying to do this. So it's going to do this probably, right? It's going to do that. So if it is doing that, then about which axis is it really doing? It's about the x-axis, right? Remember, by the way, that the plane that's, or the surface that we are evaluating is ABCD, right? So if I draw my axis again here, okay, you can imagine that this force is kind of pulling this, right? It's kind of pulling it in this direction, in the direction of the arrow that you see, about this axis that you see here. And this axis is what? X-axis. Remember that the moment occurs about an axis, okay? Not in the direction of an axis, but about an axis. So this is creating moment about the x-x axis. As a result, I have moment about the x-x axis, but I don't have moment about the z-z axis. Anytime you have like a lateral load like this, you're going to have a moment about one of the axes, right? And by the way, remember that this force that you have here cannot really be applied with eccentricity here, because if it does, then that's just torsion. Well, to put it better, it could be applied, but we're not really concerned with its effects. The only thing we are concerned with in this case is normal stresses or flexural stresses. So, we're not even like we won't be even concerned with that. It will be irrelevant for our case. So, as long as again it's applied anywhere here, doesn't matter. The effect will be the same for us. So, in this case, I will have a moment, and now I can just put the values. What is the value in this case? Well, this is 40 kilonewtons, but what is the lever arm? We always look for the perpendicular distance from the axis, right? So the x-x axis that we talked about, it was here, right? So this was the x-x axis we talked about. And what is the distance in this case? Well, the distance will be, so moment, no moment about ZZ, of course. And the distance, so this is the surface we're considering, the distance is 900 millimeters. It's from that force to the surface that we are evaluating. Okay, so you can just remember that for lateral load, it's always the distance from the kind of line of action of this force to the plane that you are evaluating, right? So this is true for lateral loads. Again, for lateral loads, your lever arm is from the line of action of the force to the plane that you're evaluating. Effectively, it is the axis, by the way. So the perpendicular distance from the XX axis is 900 millimeters. Okay? And from here, easily you can just say 40 kilonewtons times 0.9 meters. I'm going to get my moment here. And about the direction, I think this should be pretty clear because again, so we're kind of pulling it in this direction, right? It's like the arrow that I talked about here. So let's move on to our last force. And this force is applied in the kind of other direction, as you can imagine, the perpendicular direction. So in this case, it's the same idea. Again, this is kind of creating a moment. So if I draw it here, it's kind of like, again, creating a moment like this, right? And that should kind of, give us a lot of information. So as you can imagine, this is the creating kind of moment about the ZZ axis, right? So this is the ZZ axis, creating moment about that. And we'll talk about its magnitude as well. But again, as we talked about previously, lateral loads do not create any axial forces. So the axial force will be 0 here, as you can see. And the moment about the XX will be 0 as well. As you can see, again, there's no moment about XX. It's the moment about ZZ, right? The force is applied in the XX direction, but the moment is about ZZ, ZZ axis. You can also remember that if the force is applied, along the XX axis, that means that the moment is about the ZZ axis. Okay, that's not applicable to every case, but in the limitation of the questions that we're going to see in your exam, that is pretty much true. So you can imagine that if the load is applied in the XXX direction, it's going to be, the moment will be about the ZZ axis. And so, as we talked about, this will be the moment, right? Again, it's kind of trying to turn it in this direction. And how can we calculate it? Well, this is the axis that we're concerned with. The distance, the perpendicular distance, will be just from the line of action of the force to that plane that we talked about. Again, this is true for lateral loads. So from here, again, I have 1.5 meters. This one, I don't have to calculate anything because, again, you have the whole height of this block is kind of given. So 1.5 meters, I'm good to go. 30 times 1.5, which is 45 kilonewton meters. In step 3, we add all of the loads considering their direction along the longitudinal axis and about their bending axis. And let's see what we have here. So again, the total axial force. Where are we getting this from? Well, we had 4 load cases. As you remember, for 2 of them, we actually had axial force, right? So we're going to do this for both of them, for all 3 of them actually, pardon me. And in this case, from the first case, you had 15 kilonewton compression. From the second case, you have 10 kilonewton of tension, kind of pulling it. Third and fourth case, we didn't have anything, so that's that. And so we can just add them together, 15 down, 10 up, so that's just 5 down, right? So 5 down, that is my axial force. The kind of superposition of the axial forces that I had. Same thing for moment. So about about the XX axis, I had 3 kilonewton meters from the first case. I had 4 kilonewton meters from the second case. I had 36 kilonewton meters from the third case, and the fourth case I didn't have anything. So if I add them, so I have 3 and 4 in this direction, so 7 in this direction, and 36 in the other direction. So 36 minus 7, that will give you 29, right? 29 kilonewton meters in this direction. And same thing about the ZZ axis. So for the ZZ axis, you have 0.75 from case 1. You have 2 kilonewton meters from case 2. From case 3, we didn't have anything, but from case 4, we had 45 kilonewton meters in this direction. So if we add them together again, we're going to see 0.75, 2, and 45 all are in the same direction. So as a result, we're just going to say it's 47.75, as you can see here, 47.75 kilonewton meters. And that's it. So these are your axial forces, moment about the XX axis and moment about the ZZ axis. Now we are prepared to kind of calculate all the stresses for the ABCD plane and add them together, right? The normal stresses, which includes the axial stress and the flexural stresses. So in this case, we're going to find the stresses one by one. So let's see how we can do that. For axial stress, what was the formula? It's just P over A, right? So for axial stress, we have P over A, for which we have 5 kilonewtons. Remember, 5 times 10 to 3. As I always mention, for stress, the units you always want to go with is newtons and millimeter. Why? Because newtons per millimeter squared is basically just your stress, and that means megapascal, right? So, and you want to always go with megapascal because that is the most common unit that we always report our stresses in. So, in this case, 5 times 10 to the power of 3, which is converting it from kilonewtons to newtons, right? 10 to the power of 3. And also one thing I mentioned to my students is always that this 10 to the 3 is what kilo really is. It's just an abbreviation for 10 to the power of 3, right? So we just kind of feel lazy and like, okay, instead of 10 to the power of 3, we might write kilo. And that's what it really means. So you're kind of like substituting kilo with 10 to the power of 3. Or like, for example, if you have milli, you're substituting milli with 10 to the power of negative 3. And so forth, right? It's just really a substitution there. There's nothing extra that, it's not really conversion. It's just kind of, we're just replacing it. We're just substituting, you know what I mean? So that's basically how you can kind of think about that as well. So 5,000 newtons. At the bottom, you have dimension of the cross section. So the area for this kind of rectangle that you see here is 800 by 400. And from there, if you calculate it, you're going to get this much stress, about 0.015 or 0.016 megapascal. So this was the axial stress. Now, what about the normal stress, which is a resultant of the moments? So let's start with the moment about the xx axis, or the sigma xx. So in this case, for sigma xx, I'm going to have mxxz over ixx, right? Again, we already know that. One question a lot of people ask me is just, what is this z? Well, the same way, so this formula comes from my over I, basically. That's the same thing, basically. But the reason we call this z is because, as you can imagine, if this is xx, how do I measure for the my over I? How do I measure for this parameter? I always go like perpendicular from the neutral axis. So I go away from the neutral axis to the top fiber, the bottom fiber, or any layer I want. So do you see in what direction I'm moving here? So if I can show this, you see I move in this direction, or I move in this direction. Which direction was that? That was called the ZZ axis, if you remember. Okay, it's called the ZZ axis. And since we are moving in this ZZ direction, right, we just call that Z. Okay, it's just terminology, right? So the whole reason behind calling this Z is just that. And the whole reason, by the way, behind calling in the main formula my over I, why? Because we usually deal with xx and y axis. So xx is the major axis. So of course the other direction is just a minor direction, which is y. So that's why we call it my over I. So same thing for here. Our minor axis is just z. So just go with that. So mxx, z, ixx. How do we calculate all these values? For mxx, I know it. So 29 kilonewton meters. So if you remember from torsion videos, the conversion from kind of 29 kilonewton meters to Newton millimeters is times 10 to the power of 6. So I have it here. And now Z. Since I am interested in the maximum stresses that I have in my points, which is in this case B, C, D, A, I'm gonna go just with the dimension of the distance from the neutral axis to the top fiber or the bottom fiber. Again, by the way, it depends on how you look at bottom and top. I'm just relatively speaking. So to here, to side and this side. So 400 millimeters, 400 millimeters. The section is symmetric, so no worries. So I have 400 millimeters here. I'm gonna put 400 millimeters. Good. And so you have your Ixx, which is the moment of inertia about the xx axis. So as you can imagine, base is always parallel to the axis we are evaluating. Okay, so base times height cubed over 12, right? BH cubed over 12 is your moment of inertia formula, as you know from before. So I'm going to say 400 times 800 to the power of 3 over 12. And from here, I can just easily do the calculation. I have my stress about the xx axis. And lastly, I have the moment or the flexural stress about the ZZ axis. So in this case, I have 47.75. I can convert it by multiplying it by 10 to the power of 6. And then I can just mention that if this is my ZZ axis, then the maximum distance perpendicularly from this axis is just this or this, which is again symmetric, 200 from here, 200 from here. So I can put 200 there. And the moment of inertia, again, I know base is always parallel to the axis that you're evaluating. In this case, your base will be 800. So 800 times 400 to the power of 3 over 12, again, BH cubed over 12. And at the end, you're going to get your value as 2.24 MPa. And very important note here that these are just magnitudes. As you can imagine, for example, well, for this one is pretty obvious. So this is like a compressive force that you see here. So this is all going to be like in like one sign only. But you can imagine that for this one, we're going to discuss in the next page, but here you have like B and C, like one of them is like B and C are compression, A and D are tension, or otherwise, we don't know. I'm going to talk about in the next page. But something is happening. Look, these two are, one of them is like I'm pushing in, the other ones I'm pulling from, right? So the signs are going to be very significant when we're going to discuss it in the next page. So just keep that in mind. So in this case, you see that I have compression for this axial stress, right? So I'm kind of pushing it. And as you can see from here, I am pushing here for C and B, right? You see the arrow. Any direction the arrow is going, that means that I'm pushing in that direction. And I'm pulling from A and D. So I'm pulling from A and D and pushing to C and B. So as you can imagine, any push, if I'm pushing it in one direction, that means that is just, compression. If I'm pulling from something, that is just tension. And that's how you can imagine. Again, one easy kind of step that you can remember is in whatever direction the arrow is going, that means that direction, that kind of side is compression side. So that's why C and B are compression and A and D are tension. Again, same thing. Head of the arrow that you see here and the tail of the arrow. Head of the arrow, compression. Tail of the arrow is like the tension that you see. Again, I'm pushing in this one and pulling from the AD. Okay, and as you can imagine, I can't just add tension and compression like that together, So what I can come up with, however, is just some sort of sign convention. I can say, you know what? Tension is positive, compression is negative. Okay, that's one convention. Again, that's up to you completely, but again, usually that's what we go with. Now that we're done with this step, we can just form a table and kind of use the combined stress formula that we have, add the stresses together. So one step closer to the final. So here, I have all my stresses, you see. I have all my stresses, but I haven't put any signs for them, right? But I did determine which side was compression, which side was tension. So let's bring all of them up back again. So here, let's start with the axial stress. So for the axial stress, we talked about, again, it's just pushing it kind of in, right? So since this pushing it, this compression, 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 all of them, again, we are just assuming that it is a uniform distribution of stress. It's not accurate, but again, just for assumption and for using this formula, of course. And so all of them are compression. And so that's why for all of them, I'm going to put negative, 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 right? So this is the assumption we have. Compression is negative, tension is positive. So here I put negative for all of them, okay? A, B, C, D. Then I come here, as you can imagine, A and D are tension, so A and D will be positive, but B and C will be negative. So positive, negative, negative, positive. Same thing here about the ZZ. I have compression, compression, tension, tension. So A and B are tension, positive. C and D are compression, that is negative. So positive, positive, negative, negative. And at the end, I can just add them together, right? So I can just say, this plus that, that gives you the total, and so forth, right? Now that we have all of our stresses together, we can just draw the stress distribution and the line of zero stress. So in this case, I'm just going to draw my cross section, A, B, C, D, and I'm going to say, okay, I have my tension. You see, I'm just kind of pulling from the cross section, right? I'm pulling it down like that. So that is tension, right? 2.84, that is A. For B, I have 1.48 positive, that's again tension. So I'm pulling again, but again, you see, I'm can see the magnitude a little bit smaller, but it's still, again, I'm pulling down. And then for point C, I have 3 of compression. So compression, as you can imagine, will be the other direction. So just compression force. And then you have negative 1.64, which is again negative compression. And it's just a smaller value, but again, it's just going up like that. And the only thing you do after this, just connect the arrows together. So you see how I'm going to connect them? So that's the way you connect them. And after that, you're just going to put the arrows. So in the same direction, you see, the arrows are going to be put like that. Right? So you're just kind of like filling the arrows between like these cases, right? So that's how you put the arrows. And that's pretty much it. And that's pretty much your stress distribution. And lastly, you have the line of zero stress. And that's pretty much it. So simple as that. In some cases, by the way, they might ask you to determine like the distance from here or distance from here and so forth. Usually you're not really required to do that. But if you are required to do so, you can just refer back to the flexural stress video that I have for the part 1. And for example, if you remember, I have video for shear force diagram where we can determine like the X here and so forth. So you can refer back to that. I will put a link in the description. But other than that, that's pretty much it. Your question is done. And that concludes the Strength of Materials series. If you love structural engineering, you can subscribe down below. And if you have any questions about this video, you can comment them down below and I will get back to you as soon as I can. Until the next video,